Power analyzers and data loggers are essential tools for monitoring electrical parameters in various facilities. Several makes and models are available, each with its strengths and weaknesses. When selecting a power analyzer, consider the following options. Firstly, Fluke 438 series power analyzers. These analyzers are known for their high accuracy and reliability. They offer a wide measurement range for current, voltage, power, and energy. The software is user-friendly, providing excellent data visualization. Their rugged design makes them suitable for industrial environments. However, they can be relatively expensive, and additional accessories might be required for three-phase measurements. Secondly, Hioki power analyzers. Hioki analyzers are compact and portable, making them easy to move around a facility. They feature high-speed sampling rates, up to 5 megasamples per second, enabling accurate capture of transient events. They have comprehensive logging capabilities and perform harmonic distortion analysis up to the 50th harmonic. A limitation is that some models have a limited current measurement range. The software may not be as user-friendly as some competitors. Thirdly, Yokogawa power analyzers. Yokogawa analyzers are highly configurable and customizable, making them suitable for specialized applications. They offer advanced analysis capabilities, such as waveform capture and power harmonics analysis. Remote monitoring and control are possible. However, installation and setup can be complex and the cost is relatively high. Fourthly, Megger power analyzers. Megger offers cost-effective options, with models ranging from basic to advanced for different applications. Clamp-on current probes are available, making them easy to use. The accuracy may be lower than some competitors, and the software may not have as many features as higher-end analyzers. When choosing a power analyzer and data logger, keep several factors in mind. 1. Measurement range. Ensure the analyzer can measure the expected current and voltage levels in your facility. Consider the maximum and minimum values you anticipate encountering. 2. Phase configuration. Choose an analyzer that supports both single and three-phase measurements if needed. This ensures compatibility with various electrical systems in your facility. 3. Sampling rate. Higher sampling rates provide more accurate and detailed waveforms. This is particularly important when capturing transient events or analyzing harmonics. 4. Data logging capabilities. Consider the storage capacity and data format requirements for your application. Ensure the analyzer can store enough data for your monitoring period and that the data format is compatible with your analysis software. 5. Software functionality. Look for user-friendly software with features such as graphing, data analysis, and reporting. The software should allow you to easily visualize and interpret the collected data. 6. Ruggedness. Select an analyzer that can withstand the environmental conditions in your facility. Consider factors such as temperature, humidity, and dust. 7. Cost. Set a budget and compare the features, capabilities, and cost of different models. Balance your needs with the available budget to find the best value. To ensure accurate and reliable data collection, here are some tips. Calibrate the analyzer regularly to maintain accuracy. Follow the manufacturer's instructions for calibration procedures and intervals. Connect the analyzer correctly to avoid incorrect measurements. Double-check all connections before starting data collection. Allow sufficient time for the analyzer to stabilize before taking measurements. This ensures accurate readings. Monitor the data collection progress and make adjustments as needed. Keep an eye on the data being collected and make any necessary adjustments to the analyzer settings. Review the data carefully and identify any anomalies or trends that require further investigation. This can help you identify potential problems in your electrical system. Understanding electrical parameters. Effective power analysis requires a solid understanding of key electrical parameters. These parameters include voltage, current, power, energy, power factor, and harmonics. Firstly, voltage. Voltage is the electrical potential difference between 2 points in a circuit measured in volts. In alternating current or AC systems, voltage constantly changes, characterized by its root mean square or RMS value and peak value. Common voltage levels are 120 volts, 208 volts, 240 volts, 277 volts, and 480 volts. Secondly, current. Current is the flow of electrical charge measured in amps. It is also an AC quantity characterized by RMS and peak values. Current measurements are essential for determining load and identifying potential overloads. Thirdly, power. Power is the rate at which electrical energy is transferred or consumed, measured in watts. There are three types of power. Firstly, active power, also known as real power, which performs useful work. Secondly, reactive power, which supports the establishment of electric and magnetic fields. Thirdly, apparent power, which is the vector sum of active and reactive power. Power measurements are crucial for energy management and identifying inefficiencies. Fourthly, energy. Energy is the total amount of electrical work done over a period of time, measured in kilowatt-hours. Energy consumption is a key metric for billing and tracking energy usage. Fifthly, power factor. Power factor is the ratio of active power to apparent power, ranging from 0 to 1. A power factor of 1 indicates that all power is active power, while a power factor of 0 indicates that all power is reactive power. Low power factor increases losses and reduces the capacity of electrical systems. Sixthly, harmonics. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency, such as 60 Hz. Harmonics can cause distortion of voltage and current waveforms, leading to equipment overheating, malfunction, and reduced lifespan. Understanding power quality. Power quality refers to the characteristics of the voltage and current supply in an electrical system. Poor power quality can lead to equipment malfunction, reduced efficiency, and increased energy costs. Common power quality issues include voltage sags, voltage swells, transients, and harmonics. Voltage sags are short-term reductions in voltage, typically lasting from a few cycles to a few seconds. They can be caused by starting large motors while switching heavy loads. Voltage swells are short-term increases in voltage. They can be caused by sudden load reductions or capacitor switching. Transients are short-duration, high-amplitude voltage or current spikes. They can be caused by lightning strikes, switching operations, or equipment faults. Harmonics are distortion of the voltage or current waveform. They can be caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Power quality monitoring techniques. Effective power quality monitoring involves the use of specialized equipment and techniques to identify and analyze power quality issues. Common monitoring techniques include, firstly, waveform capture. Waveform capture involves recording the voltage and current waveforms over a period of time. This allows for detailed analysis of transient events and harmonic distortion. Secondly, harmonic analysis. Harmonic analysis involves measuring the amplitude and phase of individual harmonics in the voltage and current waveforms. This helps identify the sources and severity of harmonic distortion. Thirdly, event recording. Event recording involves capturing data related to specific power quality events, such as voltage sags, swells, and transients. This provides information about the magnitude, duration, and frequency of these events. Analyzing power quality data. Analyzing power quality data involves the use of specialized software tools and techniques to interpret the collected data and identify potential problems. Common analysis techniques include, firstly, time domain analysis. Time domain analysis involves examining the voltage and current waveforms as a function of time. This helps identify transient events, voltage sags, and swells. Secondly, frequency domain analysis. Frequency domain analysis involves transforming the voltage and current waveforms into the frequency domain using techniques such as the fast Fourier transform. This allows for the identification and quantification of harmonics. Thirdly, statistical analysis. Statistical analysis involves calculating statistical parameters such as average, minimum, maximum, and standard deviation of voltage, current, and power. This helps identify trends and anomalies in the data. Mitigation techniques for power quality issues. Addressing power quality issues requires the implementation of appropriate mitigation techniques. Common mitigation techniques include, firstly, surge protection. Surge protection devices protect equipment from voltage transients caused by lightning strikes or switching operations. Secondly, voltage regulation. Voltage regulators maintain a stable voltage supply, mitigating the effects of voltage sags and swells. Thirdly, harmonic filtering. Harmonic filters reduce harmonic distortion by selectively filtering out harmonic currents or voltages. Fourthly, power factor correction. Power factor correction improves the power factor of the electrical system, reducing losses and increasing capacity. Regulations and standards. Power quality is governed by various regulations and standards, such as IEC 519 and IEC 61000. These standards define acceptable limits for voltage distortion, harmonic distortion, and other power quality parameters. Compliance with these standards is essential for ensuring the reliable operation of electrical equipment and systems. Specific applications of power analyzers and data loggers. Power analyzers and data loggers are used in a wide range of applications, including, firstly, energy audits. Power analyzers can be used to conduct energy audits to identify energy waste and improve energy efficiency. Secondly, equipment monitoring. Power analyzers can be used to monitor the performance of electrical equipment, such as motors, transformers, and generators, to detect potential problems. Thirdly, power quality surveys. Power analyzers can be used to conduct power quality surveys to identify power quality issues and assess the impact on equipment and systems. Fourthly, renewable energy systems. Power analyzers can be used to monitor the performance of renewable energy systems, such as solar and wind power, to optimize energy production. Case studies. Several case studies demonstrate the benefits of using power analyzers and data loggers to improve power quality and energy efficiency. These case studies highlight the importance of data-driven decision-making and the potential for significant cost savings. Firstly, a manufacturing facility used a power analyzer to identify harmonic distortion caused by variable frequency drives. By installing harmonic filters, the facility reduced harmonic distortion, improved power factor, and reduced energy losses. Secondly, a data center used a power analyzer to monitor the performance of its uninterruptible power supply system. By identifying voltage sags and swells, the data center was able to improve the reliability of its power supply and prevent equipment downtime. Thirdly, a hospital used a power analyzer to conduct an energy audit. By identifying energy waste in its lighting and HVAC systems, the hospital was able to implement energy-efficient measures and reduce its energy costs. Future trends in power analysis. The field of power analysis is constantly evolving, with new technologies and techniques emerging to improve power quality and energy efficiency. Future trends include, firstly, smart grid integration. Smart grids enable real-time monitoring and control of power systems, allowing for improved power quality and energy efficiency. Secondly, cloud-based power analysis. Cloud-based power analysis platforms provide remote monitoring, data storage, and analysis capabilities, making it easier to manage power quality and energy consumption. Thirdly, artificial intelligence and machine learning. Artificial intelligence and machine learning algorithms can be used to analyze power quality data, identify patterns, and predict potential problems. Practical examples of power analyzer usage. Using a power analyzer effectively requires understanding its features and applying them to real-world scenarios. Let's explore some practical examples. 1. Troubleshooting motor issues. Motors are critical components in many industrial and commercial facilities. Power analyzers can help diagnose motor problems such as overload, undervoltage, or phase imbalance. By measuring voltage, current, and power, you can determine if the motor is operating within its specified parameters. If the current is higher than expected, it could indicate an overload. If the voltage is too low, it could cause the motor to run inefficiently or even fail. 2. Optimizing transformer performance. Transformers are essential for stepping up or stepping down voltage levels in power distribution systems. Power analyzers can help optimize transformer performance by measuring voltage, current, and power factor. A low power factor can indicate that the transformer is not operating efficiently, leading to increased energy losses. By correcting the power factor, you can reduce losses and improve the overall efficiency of the system. 3. Identifying lighting inefficiencies. Lighting systems can consume a significant amount of energy in commercial buildings. Power analyzers can help identify lighting inefficiencies by measuring the power consumption of individual lighting fixtures or circuits. By replacing inefficient lighting with energy-efficient alternatives, such as LED lights, you can reduce energy consumption and lower electricity bills. 4. Diagnosing HVAC system problems. Heating, ventilation, and air conditioning systems are major energy consumers in many buildings. Power analyzers can help diagnose HVAC system problems by measuring voltage, current, and power consumption. A sudden increase in power consumption could indicate a problem with the compressor or other components. By identifying and fixing these problems, you can improve the efficiency of the HVAC system and reduce energy costs. 5. Monitoring renewable energy systems. Renewable energy systems, such as solar and wind power, are becoming increasingly popular. Power analyzers can help monitor the performance of these systems by measuring voltage, current, power, and energy production. By tracking the energy production of the system, you can ensure that it is operating efficiently and generating the expected amount of power. In conclusion, selecting the right power analyzer and data logger depends on your specific needs and requirements. Consider factors such as measurement range, phase configuration, sampling rate, data logging capabilities, software functionality, ruggedness, and cost. By following the tips outlined in this discussion, you can ensure accurate and reliable data collection and analysis, leading to improved power quality and energy efficiency in your facility.